we start a new chapter called linear equations. And what we want to do in this chapter, we want to talk about the existence of uniqueness of solution for the system of linear equations that we have. So we will go over the theorems, we will see the conditions, under what conditions we have a unique solution, we have a solution at all, and we proceed accordingly. The general form of a linear equation, a linear system, is Ax is equal to B, where A belongs to R n by n, and B belongs to R n by k. And we have a theorem. Consider the system of linear equations. So consider Ax is equal to B, where A is in R n by n and B is in n by k. Let's have this on a column term, where B now there exists a solution if and only if we had the first statement before. We said when we were talking about the four fundamental subspaces, we said a system like Ax is equal to B has a solution if and only if B belongs to what?
The range space of A.
A. B belongs to R A. Two. There exists a solution for all B belonging to Rm if and only if, what do you think? Look at the number one, and then try to complete number 2. Look, what number 1 says is this. If we have a B, and this B belongs to RA, then we have a solution, right? If we have a B, and it happens that B is in RA, we have a solution. Now, in part 2, it says that for all B's, we will have a solution if
A is on 2 or not.
If
range orthogonal complement is 0? No.
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 If the range of A is all B's, in other words, whatever B we pick up, it belongs to RA. We can rephrase the number 2 in a slightly different format. We can rephrase it, and do you know if we want to rephrase it, what does it mean? If look, this is A, and this is B, right? In other words, from a space with an n dimensionality, we have the B, and A will take us to B. A takes us to vectors of B, but this time I am talking about all elements in here. All elements in here. Can you tell me that which type of function is this that I am covering? Sorry?
Und.
It's onto. So in other words, A is onto. A is onto. Equivalently, we can say that there exists a solution. Look, up to here we have not said anything new. We knew all these ones in chapter 3 and 4 and so on. There exists a unique solution if and only if we had this before. Ax is equal to b. I'll give you time to write. Just let's answer my question first. Laura, we had this. Ax is equal to b. And we said it has a solution if and only if something is equal to rank A.
Dimensionality of array. Range of A. No?
That's true, the dimensionality of A should be rank of A, but there is something else. I mean, what you will say, I will write it here, but before that, let's complete this. We had something regarding to the A, X, B in there. We said rank of A, B is rank of A, which means B is a linear combination of columns of A, right? It has to be like this. Then we have a solution, and we have value for x1, x2 till xm, and this x tells us the coefficients of linearly combining the columns in order to get B. And as Lars said, and this is possible if and only if we can say that m is less than equal than n, since m, which is the dimensionality of RA, which is the rank of A, should be less than equal to the minimum of M and N. Now if you want to write it, because I don't want to erase this part of the board. as the theorem has several parts, and I want to use this. So number 1 and 2, it was telling us we have a solution. And then we want to talk about we have a unique solution. So onto, being onto tells us we have a solution. And the next two statement is a synonym for onto, and all of these are a synonym to this. There is a unique solution if and only if
A is 1-to-1.
Let's talk about if you want to display by using these 4 fundamental subspaces. Someone said something orthogonal complement before. I don't know, it was you or what was it?
It was
What, if you want to say that it is 1-to-1,
Mhm.
what does it mean? How can we understand I? Something is 1-to-1 by considering the fundamental subspaces. If the null space of A is 0. If the null space of A is 0. In other words, A is 1-to-1. What is null space of A? 0? It means that only 0 will take us to 0. There is nothing else that takes us to 0. So it guarantees that we are 1-to-1. There exists a unique solution to the system for all B belongs to the Rm if and only if A is, okay, what about this? We knew it from high school or undergraduate algebra. This has a unique solution if A is
Both onto and 1-to-1.
which means A is,
Invertible.
which means in order to be invertible, it has to be non-singular. It's invertible. It's 1-to-1 and onto. So they are all synonyms of each other. Now, as we have the learned in the previous chapter, we can rewrite these statements. A belonging to R m by m, and A has neither a zero singular value nor a zero eigenvalue. You understand that these two are the same. Why? What will happen if we have a zero singular value or zero eigenvalue?
Smaller rank of the
Rank will be reduced. Rank will reduce. So we have like m unknowns but m minus something equations. So we cannot have a unique solution. We cannot have a unique solution. Even if we have a zero singular value or zero eigenvalue, it means that A is not singular. A is not non-singular. It is singular. Now, the fifth one that we write tells us whether we have no solution or if we have a solution, it will be the only one unique solution. And the number 4 is this.
5.
5. There exists at most one solution for all b's belonging to Rm if and only if the columns of A are linearly independent. In other words, NA is equal to 0, and this is possible if and only if m is greater or equal than n. So in other words, if we have more columns of A, more than m, and we will have a solution, only one solution, at most one solution, if they are linearly independent, if the B is combination of linearly independent columns of A. In other words, there exist columns in A which linearly depends on other columns. Because then it means that we can solve it by using, let's say, Gaussian Jordan, and then we will have columns which are 0, you can ignore them, there is no problem, and then we have enough number of equations in order to solve it. Number 6. There exists a non-trivial solution to the homogeneous system. What is the homogeneous system means? It means Ax is equal to 0. What is the trivial solution? X is equal to 0. So there exists a non-trivial, like x not equal to 0, for such a homogeneous solution if and only if rank of A is less than n. So up to now, actually, what happened was, in this theorem, we wrote what we knew from previous chapters, all in a more better classified order. So we didn't talk about anything much new. Till now, that we want to talk about a theorem which is called existence theorem. And it says that the matrix linear equation of AX is equal to B, where A belongs to R m by n and B belongs to R m by k, has a solution if and only if range of B is a subspace of range of A. In other words, there exists a solution if and only if A plus B is equal to P. And we want to prove it. And for the proof, we have to prove this. This is a two-way relationship. First, you can take this is true and prove this one, and then you have to take this is true and prove the other one, which we will do it now. We start from left to right. Suppose range of B is a subspace of range of A, and take an arbitrary X belonging to Rk, then we have Bx belonging to Rb, which is, based on our assumption, a subset of Ra. What does it mean? Bx is a subset of Ra, which means there exists a y belonging to Rn in a way that Ay is equal to Bx. There exists a y. Ra has lots of elements, but there is one element which is satisfying such conditions. Now I am multiplying both sides by AA plus. I'm multiplying both sides by AA plus. Right? And since X is an arbitrary vector, thus we understand that then A plus B should be equal to B. Why? Because what is this one? This is A. In order, because X is any arbitrary, then we need to have this term to be always true. This is A, so this term must be B. So we have to go in the opposite order. For the opposite order, I say that yes, this is true, this part is true, A plus B is equal to B. So I say take an arbitrary y belonging to RB, and then there exists X belonging to RK such that y is equal to Bx. Y is equal to Bx. Right? Now, instead of B, I write y is equal to A plus Bx. Is it correct? Because we said this is true, right? Which means that this is that. Which means that this belongs to Ra. So this means anything, because it's an arbitrary vector, anything which is a member of RB is definitely a member of Ra. So in the matrix linear equation, there exists a solution if A plus B is equal to B. And we want to use it in our next statement. Any question regarding to this proof?
Yes. The last line. Are we using the result of the first step here?
We are using this. We started from here, and we came to the conclusion that this must be true.
Okay, this must be true if this first step is true.
If
now,
this is true.
But now we assume that the second part is true.
In the second part, we say that this is true. We have to come to a conclusion that this is true. How we come to the conclusion? We say that any member in here must be also a member in here. Now, this means arbitrary y means any member in here. We prove that this is also a member of Ra. This means that there can be an element in Ra which is not in Rb. But we have to show all elements of Rb are in Ra.
So it's like the assignment question chapter 4.
Yeah. let A belongs to R n by n and B belongs to R n by k. And suppose that, can you tell me that what does it mean? A plus B is equal to B. What does it mean?
Is that how?
There exists a solution. So there exists a solution. Then in any matrix of the form X is equal to A plus B plus I minus A plus A Y. I put some space below because I want to write something later. And Y belongs to R n by K. For arbitrary Y belonging to R n by K is a solution to AX is equal to B. AX is equal to B. In a few minutes I will get back and I will write something underneath this. But how can I prove it? How can I prove it? Like, if you need to prove it, how do you prove it?
The X equal.
No, that this is a solution of this. Hassan, how do you prove it?
Maybe we just use this theory.
Like,
Put it into the
yeah,
equation.
you put this into here and you show that this is true. So let's see. AX is equal to A plus B plus AI minus A plus A Y. This is equal to, we had this big assumption. This is B plus A minus A plus A Y. What is A plus A? It is A. This is 0. So this is B. So we are proved. Now, X is equal to A plus B plus I minus A plus AY. So we have a solution, but, and the theorem was about existence. But this solution is not a unique solution. This solution is combined of, is a combination of two parts. A unique part and an arbitrary part. An arbitrary part. Why it is an arbitrary part? Don't know why this is an arbitrary part.
Because Y is...
Because Y is arbitrary. Because Y is any arbitrary matrix. And remember, this is a solution for any linear systems which we had this assumption to be true, right? So this means that we have to walk back to our traditional undergraduate linear algebra and see that whether this really holds for a very simple questions where we had a non-singular matrices. Note, when A is non-singular, a square matrix, this means that that is true. This means that then that is true. Why that is true? Then A plus is A minus, right? Minus 1, which means that this is I, B is equal to B. Always it is valid. Always it is valid. Then, now, my friends, before in linear algebra that you had in undergraduate, in high school, we had a very good square matrix, which was non-singular. And then you were solving it and you find that x is 1, x1